Now that we've considered some vector-valued functions or parameterized curves, we can see some of the challenges of trying to sketch them. We end up with this fairly tedious process of computing a table of values for each of the x's and y's and connecting those. We have lost a lot of our intuition that we would have had graphing regular y as a function of x graphs. So one of the strategies we can use is to try to be able to leverage what we did before and take what we have as a vector-valued function, or a parameterized curve here, and look at each of those components. So here we have x as a function of time is equal to t squared minus 2t, and the y coordinate is given separately by t plus 1. And what we can do then is try to eliminate the variable t from the equations, and that'll leave only x and y back in our formulation. Let's see how that plays out here. In this particular case, we can have two equations. Let's number them 1 and 2. And equation 2 leads fairly quickly to an equation for time. It's simply bringing y to the other side and t over to this side, and so we get t is equal to y plus 1. Then we sub that into equation 1, and we're going to get x is equal to t squared, but t is equal to y plus 1. So y plus 1 squared minus 2t minus 2 times y plus 1. And now what we have is an equation that relates x and y that has no t's in it. But it describes at least the points that are covered by the trajectory. We're going to dive in a little closer and see what we lose and what we gain by doing this kind of transformation. But that gives us a new form of the equation that we might be able to sketch a little more easily. Now here, it's not too obvious what the actual graph of this would look like. So let's move into an equation where you might have a little more insight. Here, we're going to start with the table of values just to reinforce how that works. And then we're going to compare it with the approach of eliminating the parameter. So here, if we look at r of t, it's negative t squared for the x coordinate and t to the fourth for the y coordinate. So for building our table, and no particular information here about size, so let's do this. Starting at negative 2, count by integers up to 2. And as we get these different values, we're going to get negative 2 squared. I have to be a little bit careful. I'll just do this one on the side. So we have negative 2 all squared. Well, that'll be negative 4. So it will be negative overall, simply because we have a negative out front of the thing that we're squaring. So we're going to have negative 4. And then negative 1, 0. When we have 1 here, we're going to have 1 squared, which is 1, with a negative out front, negative 1, and negative 4. Not too bad. Then we take a look at our t to the fourth, and that's a little more straightforward. 2 to the 4 is 16. 1 to the 4 is just 1. Negative 1 to the 4, rather, is just 1. 0. 1 to the 4 is 1. 2 to the 4 is 16. So what we're going to get from that is all the x's are negative. So we'll put our axis somewhere else. Let's put it here. And we definitely go through the point 0, 0. We go through the point negative 1, 1. The point, actually we get that point twice, interestingly. And then negative 4, 16. All right, so we'll sketch it out like so. And what we get is some kind of curve like this. And if you notice carefully, as time goes on, this is time equals negative 2. And then we move down to this point here at time negative 1. Then we hit time 0. But then we actually go back up the same curve the other way when we have time equal to 1 and time equal to positive 2. So as a trajectory, we'd walk down this curve, hit the origin, stop for a brief instant, turn around, and go back up the branch there. That would be the trajectory version of it. Now, just looking at that, feels like we should have been able to see this pattern. It looks like a quadratic, and there seem like there's even powers running around. We can highlight that or elicit that a little more clearly by eliminating the parameter here. So what we have is x equals negative t squared, y equals t to the fourth. And there's a number of different ways you can experiment with this to get rid of the t's and have just a relationship between x and y. But let's number our equations here again. And carefully, we're going to take number 1 and simply move the negative over first. And if we take it one more step, what we can do is take the square root of both sides. And you have to be a little bit careful about how to interpret this, but we'll have negative root x equals t. Now that might look a little distressing at first, but just remember that as long as what's inside the square root is positive overall, then you're okay. So this is defined only for, well, not positive x's, because we're going to then multiply them by negative, and that would be bad for the square root, but for negative x's. Take a step back to the previous page for a moment. Notice that this graph is only defined for negative x coordinates. So that actually works out. It just looks a little distressing, perhaps, when you look at that square root with an explicit minus sign underneath it. Next up, we sub that into, let's call that 3 here. Let's take 3, sub it into 2, and we're going to get y is equal to t to the 4, but t is equal to the square root of negative x. Now we're going to need to be a little bit careful with all of this. In fact, let's bring this over here so we have a little more room to maneuver. And what we're going to have is y is equal to, well, let's break this into pieces. Negative root, sorry, the negative's inside there, keep it there. So root negative x, and to the power of 4 is the same as squared and squared again. The reason we want to do that, of course, is because the square and the square root cancel each other, so we end up with y equals negative x all squared. So this 2 and that square root are inverses, they cancel each other. And then here we do end up with a net positive because this negative is inside the power. So we're going to get y equals x squared. Okay. Well, if we sketch that out, we get our classic parabola, 1, 1, 2, 4, and so on, here and here. And in fact, 4, 16, and negative 4, 16 would be off the charts here, but we would see a graph like this. And this we know, roughly, within the limitations of my sketching abilities here, we know what the shape of that parabola is. This is the classic y equals x squared parabola. Notice for here, we didn't need to sub in any values. We know what that parabola looks like. It's a classic that we've seen before, working simply with y as a function of x. In the other case, what we had to do was look at the table of values, and without a close scrutiny on all of this, it wasn't obvious that this would be necessarily a parabola. It seems somewhat reasonable, but we have to do some work to think it through, and the table of values gets us part of the way there, but maybe not as intuitively as this elimination of the parameter. So it's worth comparing and contrasting that. So the version of the approach where we had the raw r as a vector valued function or parameterized function versus the y equals a function of x, or in some cases it could be an xy relation. It might not be a function. This one here is often easier to draw because of our experience with functions y as a function of x. And that can be very handy. However, the downside is if you take a look at this parabola here and compare it both to the process we encountered along the way, this square root of negative x part, and also the part of the trajectory that we had, it can also, there's a plus sign here, a negative sign of it is that it can often include too many points. Can include some branches, is probably the best way to say it, that are not part of the trajectory, of the vector value trajectory. And just what we're capturing there is the root source of everything is the function that we're given. If we're working with that, and regardless of the t values, if we only ever end up on this branch, then that's the trajectory of this particular particle. If we never have a time value, we're on the right-hand side here of the axis, then having it in our graph here is deceptive, and we need to capture that. And we'll let you fill in the blanks here. Basically, the opposite of each of these. It's often harder to sketch the R of t. Having a table of values is probably the most systematic way to approach it, but it explicitly does include the branches and only the branches of the function that we actually traverse with the trajectory of the vector valued function or parametrized curve.